Hello, everybody, and welcome to this edition of the Ampere Developer Impact. I'm joined today by my colleague, Shiva Kintali from Ampere, and we're going to talk about a little bit the history of AI. What are the different types of AI workloads that are running on servers today, and what exactly are the compute requirements of those workloads? This is the first part of a series where we're going to dig into AI compute needs, and the punchline, as you might expect, is that Ampere is a great match for AI inference, particularly for small model LLMs and for other AI workloads like neural networks and other types of AI. But to get there, we're going to explore what exactly AI workloads look like. And in the next part, we're going to talk a little bit about the hardware that they can run on and what the various capabilities of that hardware are. And then we'll talk about how we optimize various AI frameworks for those AI workloads. So to get us started, can you talk us through a little bit some of the common AI workloads that are in use today and what those look like, where do they come from, what's going on behind the covers, and how much compute they need?
Yeah, sure. Thanks for having me, Dave. And as you said, AI has been there for quite some time, but for most people, AI is synonymous to the recent rise in GPT kind of applications, chatbot applications. But you and me, we know that AI has been there for a long time. At least I know that it has been there for at least 20 years since my undergraduate days. And it has evolved quite a bit. So if I look at the evolution of AI, it can be divided into three main generations. If I look at the first generation, I can call it as something like very foundational, where we developed algorithms like decision trees, basic linear regression, nearest neighbor algorithms, and random forests. So all those algorithms, I call them as the foundational algorithms. Okay. So that's the first generation, and they don't require too much of compute. We'll come to the actual compute requirements later. But that's what I call the first generation, which were mostly very foundational, very algorithmic, working on small data sets.
And does things like genetic algorithms, where you pick your best out of a mixture and you try it again, does that fit into first generation, or is that a little later?
Correct. Genetic algorithms, any kind of evolutionary algorithms, they all still fall in the first generation. Okay. Even some kind of very basic information retrieval also fall in the first category of the AI algorithms.
Got it.
So let's call them generation 1, right? So in generation 2 is when we started using deep learning at a massive scale. Or deep learning neural networks, they have been there since 1980s, but the application of them in a massive scale happened only in the second generation, sometime maybe in early 2010s. That's when we started revisiting these neural networks and started applying them on the massive data sets now that we have them. So that gave rise to application of applying neural networks in different contexts. For example, if you want to detect objects or any kind of objects in a vision setting, then you can use CNN, convolutional neural networks. So that falls in second generation AI.
Okay. So that's the type of AI that's used in, for example, autonomous cars and autonomous driving, right? They're detecting what objects are out there and making decisions based on that. Is that correct?
Correct. Anytime you have an image and you want to make some inference about it, who are the people, how many people are there? Let's say you go to a conference room, they have cameras to detect how many people are there for safety reasons.
Okay.
So it all started sometime in early 2010s, where people started applying this deep learning again to modern applications, and vision is one of the most common use cases back then.
Right.
So I would say CNNs, and to some extent also reinforcement learning. For example, you probably heard about AlphaGo. AlphaGo is a large-scale distributed algorithm that's focused only on solving one game, which is this Go game, right? That uses something called reinforcement learning. Again, that falls under generation 2. So generation 2 is a combination of deep neural networks and reinforcement learning.
And just because it's in a generation 2 doesn't mean that it doesn't use a lot of compute, right? AlphaGo, or what's the successor that's doing protein classification?
AlphaFold. AlphaFold.
Right. They use massive amounts of compute, correct? So it's not
Correct.
necessarily that Gen 2 means less compute. It just means an earlier version, an earlier generation.
Correct. It's like a generation 2, where, in fact, interestingly, the first time when GPUs were used for AI is when they started using them for vision applications. So GPUs started coming into the picture in this generation 2. So most of the time, in the generation 1, we were only using CPUs. There were no accelerators. So accelerators started popping up in generation 2. And then recently we had generation 3, which is much more interesting, where we have this generative AI, where we don't just analyze data anymore. Now we can not only analyze data, but also generate data, whether it is text, images, or videos, or audio. We have seen explosion of all those use cases. They're all based on this new architecture. There are different architectures. One of them is transformers. Other one is diffusion models. The third one being state space models. All these models came out in second half of 2010s, let's say 2016, 2017, that time frame. That's when people started looking at the limitations of RNNs. RNNs again fall in generation 2. They looked at limitations of RNNs and LSTMs, and they came up with new algorithms like attention and transformer architecture and diffusion models and state space models.
And just
so
for
they
my
all
benefit,
fall in generation 3.
For my benefit, RNN and LSTM stand for?
RNNs are recurrent neural networks, where you have a traditional neural network with some kind of feedback. Okay. So let's say if you're analyzing an image, you just have a static one image. But if you're analyzing a text, the text can be as long as you want, right? So you have to read the entire text to understand the dependencies.
Got it.
Maybe you have a paragraph and you have some references to the previous paragraphs. So you have a feedback loop, recurrent neural networks. And then LSTMs is a technique to make RNNs more efficient. It worked for some time, but turns out that transformers with attention are much better. So that is generation 3, transformers and ChatGPT. Everything that we see right now, all the chatbots, they fall in generation 3. Let's look at the entire spectrum, since we're talking about the generation 1 and then generation 2 and then generation 3, right? We can actually categorize them as increasingly complex models. And all of them require 3 things. One of them is more data. For example, if you go from generation 1 to generation 2 to generation 3, they all require more and more training data.
Right.
And similarly, they also require more and more compute. And they also required some kind of algorithmic breakthroughs. So that's how you categorize the generation 1, generation 2, and generation 3. Right. So if you want to look at the computational requirements for each of them, the generation 1, mostly they range from maybe anywhere from, let's say, millions of flops to all the way to billion flops.
Okay.
And if you look at generation 2, then we'll have the flops from anywhere from billion to tens of billions. And generation 3 is when you have maybe 500 billion to a trillion flops requirement based on use cases. But you asked a really interesting question there, where you said, why don't we look at only generation 3? And even within generation 3, you can categorize them into 3 parts, right? It's not that everything in generation 3 requires a lot of flops. We can categorize them into smaller models. And depending upon your applications, if you're okay with using a smaller model, they require maybe a billion or less than 10 billion flops. And if you are trying to generate something like, if you're trying to create something like AGI application, then you can have something that requires hundreds of billions or even trillion flops.
And for those who are unaware, a flop is a floating point operation. So a billion floating point operations is basically the multiplication of a lot of large matrices together, right?
That's correct. Yes.
But my understanding from, and I've only looked at a very surface level, I'm not an AI expert, but my understanding from Llama 3 with a model size like 8 billion, right? Llama 3 8B. Generating a new token, like each additional new token is about 13 to 15 billion floating point operations. You said that Gen 3 started a little higher. Does this fall into, would 8 billion like Llama 3 8B, would that count as a relatively small model?
Yeah. So roughly, I looked at multiple models and looked at the flop requirements in different settings. roughly the math works out to be, let's say you have 8 billion parameter model. The number of flops required is roughly 2 times the number of parameters.
Okay.
And that is only to generate one token, by the way.
Right.
So if you are generating, so you have to multiply it by the number of tokens. If you are generating very large text, so it will be 16 billion flops for every token that's generated.
Okay.
And that's one of the most popular techniques. And what happens is, if it must be done in a very careful manner. And if it is not done carefully, then the model can go crazy. In fact, it happened to ChatGPT, I think this year, April, May. I don't remember if it this year, last year, but it happened sometime back where it completely gave crazy answers for like 6 hours window. So these models must be monitored very properly using these perplexity measures. Perplexity is essentially you look at the token generation as a distribution of tokens, and you compare two distributions, how close they are. It's a mathematical function that measures the distance between two distributions. And you have to constantly measure them and making sure. It's called model drift, by the way. The technical term is called model drift. And irrespective of which generation algorithm you are using, model drift is one of the biggest problems in deployment. You have to constantly look at them and then give feedback and make sure that they are doing what they are supposed to do.
So we've talked quite a lot about LLMs and various sizes of LLMs and the good and bad that comes with reducing accuracy, right? But we've also covered a lot of use cases going from a few million or a few tens of millions of calculations all the way to, hundreds of billions of calculations. How can somebody who's watching this video evaluate, like, what do I need to know about my use case before deploying an AI model into kind of, an MLOps type situation, before deploying a model to production and unleashing it on my customers? Like, how do I figure out how much compute that's going to need, and then use that information to match it up with the right hardware platform?
Yeah. So essentially, the very first thing you need to do is look at your application and look at your use case, and first figure out which generation it falls in, right? And frankly, if it falls in generation 1, as I mentioned, there are very well optimized algorithms even that can run even on just traditional CPUs, right? And then see if it falls in generation 2. For example, if you are doing video analytics or image analytics, that falls in generation 2. And then if you're doing language modeling, then of course falls in generation 3. First look at them and then understand where it falls and what kind of models you are trying to use. So once you figure those out, try to figure out what are your SLAs. For example, the very first thing is latency, right? Let's say there's a customer who is talking to you, like how much latency can they tolerate? I mean, just last week I was talking to Xfinity or some Comcast kind of customer chatbot, and I was really pissed off that it made me wait for a long time. So you have to really make sure that what is the latency? You ask a question and then it waits for you have to wait for 5 seconds. So that's your latency, right?
And then the requirements on something like a Tesla self-driving car are going to be pretty low, right? You need to be able to react within tenths of a second if something happens.
Exactly. So
can't afford to wait 3 seconds, right?
Yeah, and on other extreme, so on one extreme we have this very real-time applications where you want instantaneous answer as fast as possible, and on the other hand you have some workloads where you really don't care about live interaction. For example, let's say you are IMDb website, and you're trying to analyze the sentiment of all the movie reviews, right?
Right.
And that can be done overnight in a batch mode, right? It's not you don't need interactive token generation there, right? So there your SLA requirements are much low. So you have to look at what's your latency, what is the number of tokens per second if it's a language generation model, and what is the number of frames per second that you want to analyze if you are looking at video analytics or image analytics.
Okay. Right. So once you've understood what your model looks like, what generation it's in, how much calculations per second it needs, then the SLO service level objective that you have in terms of like how fast it needs to respond and how accurate the response needs to be. What's the next step?
So the next step is to identify, of course, you need to look at your current infrastructure and see what kind of infrastructure do you want to build for the long term. So let's say, is it a multi-core solution. For example, that's what we provide at Ampere, right? So most of this, for example, you talked about the smaller models. Most of the smaller models and medium-sized models, they can be run very efficiently on Ampere, just
Right.
using multi-core CPUs without using any accelerators.
Okay.
So that is our first decision. Can I do all these things using a multi-core CPUs? So Ampere can do all these small and medium language models, and we can also do YOLO kind of CNN models running very efficiently on just CPUs, right?
Right.
And then if you have applications like very large scale token generation or large scale video analytics where you want to have, let's say, 5,000 frames per second, then you need an accelerator. And you need to figure out what kind of accelerator you need on top of Ampere multi-core CPU. And even after that, even after you make the decision, there are more decisions that you need to make about which algorithms to run on CPU and which algorithms to offload to an accelerator. I mean, think of it as, optimizing the resources, right? You have multi-core CPU, which is very powerful. Let's say in the case of Ampere, one of our solution hardware has something like 192 cores, and you have an accelerator. And for example, if you look at image generation, right, this accelerator can do only one thing, which is you are given an image, it will tell you what are the objects that are present in that image. That's all it can do, nothing else, right? So it's like a beast that can only solve one problem. Now everything else must be done on the CPU. So it's your job to optimize everything else, whether it is queuing all these frames, splitting them into multiple frames, and sampling them, and changing the resolution, whether it's upsampling or downsampling. You have to do everything, all of that on the CPUs, right? So you have to optimize your algorithms properly and make sure that you are only doing using the accelerator only for that particular purpose, whether it is running a particular CNN model or running a particular LLM.
Well, so in this episode, we have reviewed what the compute requirements are of various generations of AI and machine learning models. We've talked about some of the history of AI, what compute requirements those different AI generations have, how some of the ways that those models can be optimized when running in production, and we've talked a little bit about how you figure out what your service level objectives are for your AI workload. How quickly do you need answers, and how accurate do those answers need to be? In the next episode, in the next interview, Shiva, that we do together, we're going to talk a little bit more about the hardware options. Why do we hear so much about accelerators? What are the performance characteristics and price performance characteristics of AI accelerators like tensor processing units and general graphical processing units or GPUs? But so we're going to talk about some of the hardware characteristics and CPU, like why from a perspective of, for example, memory bandwidth and calculations per second, accelerators are required for some of those big workloads, and also when you can figure out like what exactly the performance characteristics are of CPU and when you can use that for these types of workloads. So thank you very much for joining me today. I'm really looking forward to our next conversation on this topic, and I look forward to seeing you all on a future edition of the Ampere Developer Impact.
Thank you, Dave. Looking forward to the next one.